Number 1, we have the distribution curve, and the question says that what happens if we add an effective catalyst. What a catalyst does is it will actually lower the activation energy required. So this is the energy level or the activation energy without the catalyst. With the catalyst, you expect the activation energy required to be on the left, right, lower than before. The shape of the curve will not change because there's no change in the temperature of the system. So the height of the peak remains the same. Activation energy moves to the left. Number 2, which gives the best indication of strength between the hydrogen bonds. Hydrogen bonds will be across molecules. So if we have the halides, this is one molecule, HX, this is another molecule, partially positive, partially negative. The hydrogen bonds will be from one molecule to the other. So how strong this is, we can see from enthalpy change of vaporization, right, which is essentially changing the liquid state into a gaseous state. So we are separating molecules from each other. The harder it is to separate, the higher will be the enthalpy change of vaporization, the stronger will be the hydrogen bond. Right. Dissociation, bond dissociation energy, if you to consider A, bond dissociation energy is actually talking about the strength of the HX bond within the molecule. We are not breaking this, or this is not the hydrogen bonds. Right, so we are breaking the hydrogen bonds. It will be the vaporization enthalpy change. Number 3, we are burning carbon, and half a gram will turn carbon into carbon dioxide, another half gram will form carbon monoxide. We pass both of them into excess sodium hydroxide. Remaining gas is dried and collected. Well, if we pass both gases through sodium hydroxide, the sodium hydroxide will remove the acidic carbon dioxide. So when they say remaining gas, what they are actually trying to ask is how much carbon monoxide was collected. Okay, so we just have to figure out half a mole or half a gram of carbon monoxide, or half a gram of carbon, how much carbon monoxide will it form. So we have an equation here. Half a gram of carbon, you find out the number of moles for carbon, 0.5 divided by the AR. Okay, so 0.5 over 12, that's the number of moles. That will be the same number of moles for carbon monoxide. And if you want to find the volume, we take the number of moles of carbon monoxide multiply by 24 dm cube, okay, because it is at room temperature pressure. Right, we get 1 dm cube. Question 4. Which one is oxidized and which one is reduced? So a quick allocation of all the oxidation states of the elements. Oxygen in the oxygen difluoride. Since the fluorine has -1 in this compound, it will mean that the oxygen is +2 here. And then we've compared to the end, the oxygen here will have a -2 each. Right. Be aware that I'm just calculating each oxygen, not the total. So do not put -6. So oxygen +2 becomes -2 oxidation state. It is reduced. We compare the fluorine. It was -1 as stated. Okay, -1 each, and then it goes to become an element. It becomes 0. So the fluorine was oxidized. Right. That actually gives us the answer B. If you want to check the sulfur, -4 or +4, it becomes +6. So the sulfur was oxidized. Number 5, we have a gas equation, PV equals to nRT, and we are given information, so we have to convert the units, the numbers to the correct units before we can use the equation. Grams of oxygen gas, we divide by its mR to get number of moles. Volume, we can leave it as cubic meter. Temperature, degrees Celsius, we have to convert to kelvins. So once we have all these units, we will put inside the equation where pressure is the unknown, or pressure is the subject. Moles, gas constant, temperature over volume. This will give us a pressure in terms of Pascal. Then we convert to kilopascal. For question 6, we have this equilibrium, and the experiment was carried out twice at different volumes. What was same for the two experiments would be the temperature, and not explicitly stated, but you have to realize it's also the same will be the external pressure, meaning the system will reach an equilibrium or reach a pressure that's the same as the external pressure. So pressure for the first experiment is actually the same as the pressure for the second experiment. So P1 equals to P2. We can use the gas laws again, expression, and put as nRT1 over V1, number of moles for T2 over V2. Some of the variables are the same, gas constants and the temperature. There's no change for the experiments. And then we know that V1 and V2, we have actually the numbers 1 dm cube and 2 dm cube respectively. So if you were to simplify, we actually have number of moles for the first number of moles of gas for the first experiment is half the number of moles of gas for the second experiment. In other words, you have more moles of gas in the second experiment. That's the important thing. So what does it mean for the equilibrium? How will we get more moles of gas? It means the equilibrium shifted to the side that produces more gases. Right here, we have one molecule. On the right side, you have two molecules. So it means the system actually produces more of the products, because experiment 2 contains more moles of gas. So it shifted to the right. You have less PCl5 compared to the first experiment. Question 7. Standard enthalpy change of glucose and ethanol. So this is the equation where the conversion takes place. What's the enthalpy change for this reaction? For this reaction, we can use the general equation where heat of reaction is heat of combustion of reactants minus heat of combustion of products. So for reactants is given 2820 negative. The products, we have 2 moles of your ethanol, so we have to multiply by 2 and we subtract it. Oh, I missed out the negative sign here. Right, minus 2 times heat of combustion of your ethanol. There's no heat of combustion for your carbon dioxide. Right, it's already fully oxidized already, so we do not need the value for carbon dioxide. So once you have this equation, you will get negative 84 for your heat of reaction. Number 8, in which reaction is the underlying substance acting as a base? Acting as a base, one way you can look at it is it accepts hydrogen protons. So a quick comparison of the options we have. This underlying substance actually loses hydrogen protons to form HSO4 minus. So this one is actually acting as an acid for option A. HCN loses hydrogen protons, so it is still an acid also. HCO3 minus, right, it might not be obvious what we can compare to. There are a few ways we can compare. We can compare to the carbon dioxide. You can see that it loses OH minus, so that's also one way we can see that it's acting as a base. One more way we can conclude will be looking at the other sub-reactants. Right, HNO2, we can see that HNO2 is the one that loses a proton because it forms NO2 minus. So HNO2 is an acid. It loses a hydrogen proton. HCO3 minus is actually the one accepting a hydrogen proton. Okay. That's actually a intermediate. It gains a hydrogen proton. It actually forms H2CO3, and then this one is not too stable. It will actually break into hydrogen, or it will break into water and carbon dioxide. So the proton acceptor is the underlying substance here. Okay. If you can eliminate D also. D is a hydrogen proton donor. It loses hydrogen to form this substance here. So the underlying substance for D is also an acid. Number 9, we have this equilibrium, and they tell us that the equilibrium concentration for oxygen 7.6 times 10 to the power minus 6. So the equilibrium concentration respectively will be X, unknown, X here because they say that these two substances are equal, so X and X. Oxygen is the only number that we know, and then we create the Kc expression, concentration of products over reactants. Oxygen, we have to put it to the power of 4 because of this coefficient here. And we substitute the values in, you will realize that your X, although we do not have the numbers, it doesn't really matter because they will cancel each other out. So finally we have the Kc here. Using your calculator will give you option A. Number 10, we have an ethene molecule. So this is an sp2 hybridization. sp3, if you're wondering, sp3 will be for carbons that have 4 single bonds. Then this will be sp3. So the options sp3 will be out. It will be sp2 for one of the sigma bond, for the sigma bonds here and one of the sigma bonds here. The other bonds in a double bond will be a pi bond. Right, that's where the sideway overlaps of the orbitals come in between these two carbons. So answer is A. Number 11. Which arrow represents activation energy for the forward reaction? So for the forward reaction, we start from the left side, and this is the amount of energy the particles have to attain. So B will be the activation energy for the forward reaction. For comparison, C will be the activation energy for the backward reaction, right, for the products to go back into the reactants. This is the amount. D will be actually the enthalpy change. Number 12, electrolysis of brine is actually concentrated sodium chloride solution. So why do we need to keep the other chemicals separate? A quick look at the cathode and the anode. At the cathode, your water molecules will be oxidized, or water molecules will be reduced to form hydrogen gas and leaving behind hydroxide ions. The anode, your chlorides will form chlorine gas. Right. If we do not have a membrane, your hydroxides will react with your chlorine gas. In the reaction below, sodium hydroxide, right, sodium is left behind, sodium hydroxide will react with chlorine gas, and we'll get sodium chloride and sodium hypochlorite. That essentially means we are losing the products of chlorine which we are aiming for. So we have a membrane, okay, to prevent the hydroxides and the chloride and the chlorine gas from reacting with each other. We have three minerals, and when they are heated, they decompose to produce carbon dioxide gases, and then this gas will be the one that's responsible for putting out the fire. So the trend that you have to be aware of is the ease of decomposition. For your group 2, as we go down the group, it will be harder to decompose. In other words, it'll be harder for barium carbonate to produce carbon dioxide. Among the three, magnesium carbonate releases carbon dioxide the most effectively. So magnesium carbonate is the most effective mineral or component in the mineral to put out the fires. So if you compare the three minerals, the third mineral has a larger proportion of magnesium carbonate. So this third mineral will be the best. The second best will be the second mineral. It contains magnesium carbonate and calcium carbonate. The third most effective will be the first mineral, because it contains carbonates that do not decompose as easily as the magnesium carbonates. That's why we have option D. So compare which one releases carbon dioxide the easiest, and that will be the one that will be the best mineral to use to put out fires. What is observed when we add a sample of silicon chloride to water? This reaction will take place. It will form silicon dioxide, which actually will be a white precipitate, a white powder, and then you have hydrogen chloride fumes, right? The steamy fumes. So option will be B.